Let's say at the beginning we have this graph of cosine curve multiplied by a Gaussian curve. This is the function u at time 0. Also at the beginning, let's say this function u x, t follows this equation, partial differential equation. Also, let's add a solid wall as the right boundary. And we want the function u to be always 0 on the wall, that is, for x greater than 8. At time positive t, we want the dynamics of the function u to follow this partial differential equation, that is, the wave equation. What you see here is the numerical solution to our wave equation, solved using Fourier Transform. You can see that the waves are reflected against the wall. Okay, so how do I make this numerical simulation using Fourier Transform? We will learn about solving various scenarios of wave equations using Fourier Transform. The general wave equation has a coefficient c squared in front of the x partial derivative. The absolute value of c is called the wave's constant speed. The wave will travel at a constant velocity c. Here is a simple illustration. After some point in time t equals 1, if c is 1, then the wave will have traveled of distance 1. If c is 10, then the wave will have traveled of distance 10. For simplicity, in this video we will use the unit speed c equals 1. This video is divided into 3 parts. First one is Fourier Transform origin. This is important because we will know the building blocks of the PDE solution. Second one is the exact solution of the 1D wave equation in the infinite domain using Fourier Transform, also called the D'Alembert solution. Third one is numerical solution of the 1D wave equation using Fourier Transform in various scenarios. This is planned to be discussed in an upcoming separate video. In this section, we will talk about the origin of Fourier Transform. There are 2 versions of Fourier Transform. This one, on finite domain, is used when we only want to transform the function on the open interval from -L to +L. This one is used when we have the function fx defined on the whole real line, when we take the limit of the open interval as L goes to +infinity. Either version, when we use the transform, we always assume that the function fx is represented by the Fourier series. This is the Fourier series. It is a linear combination of sine and cosine waves with different amplitudes ak and bk, with different frequencies small omega k equals k pi over L. Any continuous or piecewise continuous function defined on the interval -L to L can be written as Fourier series. Example of piecewise continuous function. The proof won't be discussed here, but the curious viewers may want to check this book for detailed and friendly proof. The coefficients or the amplitudes must follow these relations. Of course, the value of the coefficients depends on the function fx. We can write the inputs of cosine and sine as 2 times k times pi times x over 2l, and it immediately shows that the cosines and sines are 2l periodic. The whole series must also be 2l periodic. Thus, the Fourier series can be extended indefinitely. This is the periodic extension of the Fourier series, not the function fx. Then we can actually extend it to infinity. Since Fourier series is periodic with period of 2l, then a numerical solution of a wave equation via Fourier transform will also have periodic solution. This is true if we don't add conditions at the boundaries. In this example, the period is 20, and you can easily see that each boundary is like a door to go through to the other boundary. Let us see this in more clarity. The numerical solution is written in Fourier series, and we can see clearly here that the periodic boundary is the result of periodic extension capability of the Fourier series. Let us see examples of Fourier series convergence. This is the continuous one. You can see as the number of Fourier terms increase, the series converge to the function at the open interval from -3 to 3. You can see at the boundaries they do not guarantee convergence. This is the piecewise continuous example. The animation speaks for itself. As n goes larger, the series converges to the function. This is an example of more arbitrary piecewise continuous function. The interval is from -5 to 5. You can see the Fourier series approximation here as the number of sine and cosine terms increase. The series converge to the piecewise function. To see how we can get to Fourier transform, we must write the Fourier series in the complex form. It is not difficult to obtain this form. We write the cosine and sine in complex form, and then plug into the Fourier series. After a little rearrangement, we can get this form. Notice that b0 is just equal to 0 because of the coefficient formula. Sine 0 is 0. Next, cosine is an even function, so the ak is actually equal to a with index minus k. Similarly, sine is an odd function. It is easy to see that the coefficient bk is equal to minus of b with index minus k. Using this result on the second summation here, we can attain a summation with index from -1 to -infinity. Combining them all, we get the Fourier series in complex form. And we write ck to be ak minus bk times I over 2. The new coefficient ck still depends on the ak and bk from the previous form. So we have learned a brief about Fourier series. But how can we get to Fourier transform? First, let's write the k pi over L as 2 pi k over 2L. Then let omega k as k over 2L. Then let delta omega be the difference between frequencies. Now write the coefficient in the integral form by the following simple algebraic process. This is the integral form, and now put it on the series. Now put delta omega over delta omega here. So we get this form. Next, define f hat to be this integral from minus infinity to plus infinity. And as L goes to infinity, we have delta omega goes to 0. So we have this Riemann sum transformed into an integral. And the integrand is f hat times the exponent. And this one is what we call the Fourier transform. The other one is called the inverse Fourier transform of f hat. For convenience, let's use small omega notation as the frequency variable. Now, how can we use Fourier transform to solve a wave equation? Consider a specific problem where we will solve the wave equation on the whole real line. So in this case, there is no boundary condition. Let the initial wave be a Gaussian curve. Next, let the second initial condition be this. The first derivative of u with respect to t equals 0. Here is a spoiler. The solution wave will split and travels in two directions. This is the solution at time t equals 1. You can see the wave split. And this is at the time t equals 5. Since there is no boundary condition, the two waves will just keep traveling forever. Let us prove this. The idea to solve this is that we write the solution u as the inverse Fourier transform of this function u hat. U hat is the Fourier transform of the solution u. Now let us write the wave equation in terms of Fourier transform. We also need to write the second partial derivatives. We can use the Leibniz integral rule here, which says that differentiating an integral is the same as differentiation under the integral. We can extend this and use the rule as the limit L goes to infinity. So this rule also applies even if the domain is unbounded. So the second partial derivative with respect to t will be just differentiating the u hat twice, because it is the only one that depends on t here. Similarly, for second partial derivative with respect to x, we just differentiate this exponent twice. Now we plug in these results into the wave equation. This is the transform wave equation. It is in integral form. We can simplify further to get this nice form. Notice that this equation is solved if we extract the integrand and this equation equals to 0 is solved. If we assume omega is constant, then this is just an ordinary differential equation on the variable t. We have this new equation, and this transformed wave equation is much simpler and easier to deal with than the original wave equation. This is the initial condition of the wave equation. Now for the initial condition in the frequency domain, it will be just the Fourier transform of the original initial profile. F hat is the Fourier transform of the function fx. For the second initial condition, we can write u as the inverse Fourier transform and then use the Leibniz rule again to get this transformed initial condition. This ODE has the same form as this one, which can be easily checked that it has solution k times cosine r times t. Comparing to the transform wave equation, the solution of this ODE must be this, f hat times cosine 2 pi omega t. We have found the exact solution of the transform wave equation. But this is the transform solution. To find the original solution, we first write the cosine in complex form, and then we apply inverse Fourier transform to get to the original solution u. Luckily, this is not hard. We can look at the Fourier transform table on Wikipedia here, and we will look at this one. The appropriate one is this one right here. So the inverse Fourier transform of f hat times this exponent must be fx minus t. Thus, we can immediately see that the inverse Fourier transform of u hat, that is the transform solution, will be just half of fx plus t and then plus fx minus t. So we have found the exact solution of the wave equation on infinite domain. Also called the D'Alembert solution. If the initial is Gaussian, this is the solution. You can see each wave is either fx minus t or fx plus t. Both waves traveling to different directions. Let us see more interesting examples with different initial wave. We have here 3 Gaussian curves in different positions. And this is the dynamics. You can see there are waves traveling to the right and 3 waves traveling to the left. Here we have an initial condition of the sum of 2 cosine waves with slightly different frequencies. The above and bottom are the components of the exact solution. Above is traveling to the right, below is traveling to the left. Here is the dynamics. Let's try another one with initial state of 3 cosine waves with slightly different frequencies. For more complex wave equation with different boundary conditions, like the example you see at the intro of this video, we can use numerical simulation to approximate the exact solution. This is planned to be discussed in an upcoming video.